We are solving question number 36 of GATE 2020 Chemical Engineering paper. A student performs a flow experiment with a Bingham plastic under fully developed laminar condition in a tube of radius 0.01 meter with a pressure drop of 10 kilopascal over the tube length of 1 meter. The velocity profile is flat for R is less than RC and parabolic for R greater than RC as shown in the figure. Consider R and X as the radial and axial direction, and the shear stress is finite as R approaches 0. A force balance results in the following equation, where tau Rx is the shear stress. If RC is 0.001 meter, then the magnitude of yield stress for this Bingham plastic in Pascal is dash. So over here we have been given the velocity profile of the Bingham plastic. So, and here we can see that this is the radial direction and this is the axial direction. And until this R tends to for R less than RC, we are having this constant velocity profile. And if R is greater than RC, then we are getting somewhat kind of parabolic velocity profile. That implies that beyond RC, there will be the shear stress is sufficient enough to develop for the Bingham plastic to fluid. That implies that at R equal to RC, there will be this yield stress above which the Bingham plastic will start to flow. So basically we have been asked to find the shear stress at RC, that is the yield stress tau naught. So for that we need to find the relation between the shear stress tau Rx with respect to R. This tau is a function of R. So what we will do is we can simply integrate this equation and get the desired relation. So to integrate this equation, we can write this as integration of d into R into tau Rx is equal to integration of R minus delta P upon R into dr. So if we integrate this, we will be getting R tau Rx is equal to delta P upon L will remain constant. Integration of R will be R square by 2 plus some constant. So we can also write this as tau Rx is equal to minus of delta P upon 2L R plus C upon R. Now from the given information, we need to find the value of this constant C. So in the question, we can see that we have been given that the shear stress is finite as R approaches 0. That is, as R tends to 0, tau will become finite. Tau Rx will become finite. So we can put R equal to 0 in this equation. So if you put R equal to 0, this term will become 0. So, and since this is finite, that implies C must be 0 for this equation. So for both the sides to be finite, that implies the value of constant C is 0. And from this, we can get the correlation as tau Rx is equal to minus of delta P upon 2L into R. So now we have to find tau naught, which is basically tau Rx at RC. So tau Rx we found out as minus of delta P upon 2L into R. So if you put R equal to RC, then we will be getting the yield stress, that is tau naught. So delta P we have been given as 10 kilopascal and length we have been given as 1 meter and critical RC is 0.001 meter. So delta P was 10 kilopascal. The length is 1 meter. Radius is 0.001 meter. This unit will get cancelled out. And we will be having 5 into 10 raised to minus 3 kilopascal. That implies the yield stress. If we neglect the sign, so it will be 5 Pascal. So the final answer, that is the magnitude of yield stress for the Bingham plastic, is 5 Pascal.